Recursive algorithm analysis. I'm Efina and I'll be presenting you this topic. The topics of discussion in this presentation are the recursive algorithm explained with an example, an introduction to recurrence relation and types of recurrence relation, because recurrence relation are used to represent the recursive algorithm mathematically, and finally we solve the linear recurrences and nonlinear recurrences to obtain the time complexity of a recursive algorithm. Recursive algorithms contain a call to itself. A classic example of recursive algorithm is finding a factorial of a non-negative integer. The algorithm fact n gets a non-negative integer n as input. The output of the algorithm fact is the factorial value of n. The algorithm contains a if-else statement in which if n equals 0, it returns a value of 1. When n is greater than 0, the algorithm calls itself with the reduced value of n and multiplies it with n. As you notice, this algorithm contains two cases. The first one when n equals 0, the other one when n is greater than 0. When n equals 0, the algorithm stops the recursion, and it is called the base case. When n is greater than 0, the algorithm calls itself with the reduced value of n, and this is called the recursive call. Subsequent recursive calls work towards the base case. How do you analyze a recursive algorithm? Recurrence relation is used for analyzing the recursive algorithm. The steps to be followed are: formulate a recurrence equation to represent the recursive algorithm, solve the recurrence equation to determine the order of growth of the recursive algorithm. The recurrence relation is of two types: linear recurrences and nonlinear recurrences. Let me explain the linear recurrence and the nonlinear recurrence. The linear recurrence equation for a sequence t suffix 0 to t suffix n expresses the final term t suffix n as the linear combination of the previous terms. Linear recurrences represent the recursive algorithm that contains a recursive call with linear reduction or in their input. Hence, the factorial algorithm could be represented as a linear recurrence equation as t suffix n equals n multiplied by t suffix n minus 1. The nonlinear recurrence equation for a sequence t suffix 0 to t suffix n expresses the final term t suffix n as the nonlinear combination of the previous terms. Nonlinear recurrences represent recursive algorithm that contains recursive call with nonlinear reduction of their input, like a merge sort, where the recursive call to the merge sort is performed with half the value of the original array. The example of a nonlinear recurrence is given as t suffix n equals a multiplied by t of n divided by b plus f of n, where n divided by b is the size of the subproblem, which is nonlinear. Let us see few examples of recurrence equation representing the recursive algorithm. The recurrence equation of the recursive factorial algorithm is t suffix n equals n multiplied by t suffix n minus 1 for n greater than 0. The recurrence equation for the algorithm computing the sum of the cubes as 1 cube plus 2 cube to n cube is given as t suffix n equals n multiplied by t suffix n minus 1 plus n cube for n greater than 0. How do we find solution for linear recursion that represents the linear recursive algorithm? Let us solve a linear recurrence equation. The recurrence equation t suffix n equals t suffix n minus 1 plus 3 represents a recursive call in a recursive algorithm. T suffix 1 equals to 4 represents the base case in the recursive algorithm. To solve that, we substitute the t suffix n minus 1 by the definition of t suffix n as t suffix n minus 2 plus 3. Again, we substitute t suffix n minus 2 with the definition of t suffix n as t suffix n minus 3 plus 3. Generalizing, it could be written as t suffix n minus k plus k multiplied by 3. When the value of k is substituted as n minus 1, Tn equals T1 plus 3n minus 3. Substituting the value of T1 equals 4, T suffix n equals 1 plus 3n, which is the time complexity function of the linear recursive algorithm that is represented by the linear recurrence equation t suffix n equals t suffix n minus 1 plus 3. Let us solve the linear recurrence equation that represents the recursive function of finding a factorial of a given number n. The recurrence relation is given as t suffix n equals n multiplied by t suffix n minus 1. Repeatedly substituting the value of t by the definition of t suffix n, the general formula of the kth step could be obtained as t suffix n equals n multiplied by n minus 1 multiplied by n minus 2, which extends to n minus k multiplied by t suffix n minus k minus 1. Substituting the value of k by n minus 1, we get the value of t suffix n as n multiplied by n minus 1 multiplied by n minus 2 extends to 1 multiplied by t 0. Since t suffix 0 equals 1, t suffix n equals n factorial, which is the time complexity function of the factorial algorithm that makes a recursive call to itself. How do we solve a nonlinear recursion that represents a nonlinear recursive algorithm? There are two methods to solve the nonlinear recursion, which are the recursion tree method and applying the master's theorem. Recursion tree is useful for visualizing what happens when a recurrence is iterated and subsequently solving the nonlinear recursive relation. Let us take the example of a nonlinear recursion as t of n equals 2 multiplied by t of n by 2 plus n. The given nonlinear recurrence relation shows the problem size of n will be divided into two subproblems of size n by 2 and so on. This represents the recursive call in the nonlinear recursive algorithm. The base case, which will be represented as the bottommost layer in the recursion tree, has the size of the subproblem be reduced to 1. Visualization of recursive part of the nonlinear recurrence relation is as given here. The recursive part in the nonlinear recurrence relation was given as 2 multiplied by t of n by 2, which is the problem size of n is divided to n by 2 at each recursive call. If t of n represents the root node, its children are represented at level 1 as t of n by 2. The children of t of n by 2 are t of n by 4, and this proceeds to the leaf level. To solve the nonlinear recurrence relation that is represented by the recursion tree, we need to determine the total number of levels in the recursion tree and also the cost at each level. Let us determine the total number of levels in the recursion tree. The size of the subproblem at level 0 equals n divided by 2 power 0. Similarly, the size of the subproblem at level 2 equals n divided by 2 power 2. Generalizing, the size of the subproblem at level k equals n divided by 2 power k. Since the base case equals 1, the size of the subproblem is reduced to 1 at the leaf node. Hence, n divided by 2 power k equals 1, which could be simplified as k equals log 2 of n. Hence, the total number of levels in the recursion tree equals log 2 of n plus 1. Let us determine the cost at each level of the recursion tree. The cost at level 0 equals n. The cost at level 1 equals n by 2 plus n by 2 equals n, where n by 2 represents the cost for each child at level 1. Similarly, it proceeds till the leaf level in the recursion tree. Hence, the cost at each level of the recursion tree is n. So, the cost of all levels in the recursion tree equals n multiplied by log 2 of n plus 1, where log 2 of n plus 1 is the height of the tree. The cost of the recursive part of the equation Tn equals n multiplied by log 2 of n plus n. The cost of non-recursive part of the equation T of n equals n. Hence, the total cost of the nonlinear recurrence relation represented as T of n is n multiplied by log 2 of n plus n plus n. Applying the sum rule, we could say the time complexity of the recursive algorithm that is represented by the nonlinear recurrence relation as theta of n multiplied by log 2 of n. Let us see another example for solving the nonlinear recursive algorithm using a recursion tree. The recurrence relation is given as T of n equals T of n by 3 plus T of 2n by 3 plus n, which represents the problem size of n is divided to n by 3 and 2n by 3. Hence, the recurrence tree for representing such a recurrence relation is as given here. N is the root node of the recursion tree representing the size of the problem. It is divided at level 1 to 2 children as n by 3 and 2n by 3, which represents the size of the subproblem. This is proceeded until the leaf node of the recursion tree. To compute the cost of the problem, we have to determine the total number of levels in the recursion tree and the cost at each level of the recursion tree. So, the size of subproblem at level 0 equals n divided by 3 by 2 power 0. Similarly, the size of subproblem at level 2 equals n divided by 3 by 2 to the power 2. Hence, the size of the subproblem at level k equals n divided by 3 by 2 power k. The problem size is reduced to 1, representing the base case. Hence, n divided by 3 by 2 to the power k equals 1, and taking log on both sides and simplifying, k equals log of 3 by 2 n. Hence, the total number of levels in the recursion tree equals log of 3 by 2 n plus 1. Let us determine the cost at each level of the recursion tree. The cost at level 0 equals n. The cost at level 1 also equals n, which is obtained as the total of the cost of all the subproblem at level 1. Therefore, the cost at each level of the recursion tree could be deduced as n. The cost of all levels in the recursion tree equals n multiplied by log 3 by 2 n plus 1, where, as we know, log 3 by 2 n plus 1 is the height of the recursion tree. The cost of the recursive part of the recurrence equation Tn equals n multiplied by log 3 by 2 n plus n, which we obtain using a recursion tree. The cost of non-recursive part of the recurrence equation Tn equals n. Hence, the total cost of the recurrence relation Tn equals n log 2 of n plus 2n. By applying the sum rule, the time complexity of the recursive algorithm represented by Tn equals theta of log n. Let us solve the nonlinear recurrence relation using the master's theorem. The nonlinear recurrence relation T of n is given as a multiplied by T of n by b plus f of n. For applying the master's theorem, we derived the variable d from the time complexity of f of n, where f of n is an element of theta of n power d. The master's theorem states that T of n is an element of theta of n power d if a is less than b power d. T of n is an element of theta of n power d multiplied by log n if a equals b power d. T of n is an element of theta of n power log a base b if a is greater than b power d. The similar results hold for big O and big omega notations also. Master's theorem cannot be used to find the time complexity of the algorithm represented by the nonlinear recurrence relation T of n when T of n is not monotone, or when f of n is not a polynomial, or when b cannot be expressed as a constant. An example for each of the case is as given here. Also note that Master's theorem does not solve a recurrence relation. Master's theorem finds the time complexity of the algorithm that is represented by the recurrence relation T of n. Let us apply the Master's theorem to the recurrence relation T of n equals 9 multiplied by T of n by 3 plus n to obtain the time complexity of the recursive algorithm represented by this T of n. From the recurrence relation, it could be deduced that a equals 9 and b equals 3 and d equals 1. The value of d is obtained from the non-recursive part of T of n, which is n. So, applying the Master's theorem for the case a greater than b power d, we obtain the time complexity of the recursive function as theta of n square. Let us see another example of applying Master's theorem to find the time complexity of the recursive algorithm from the recurrence relation T of n that represents the algorithm. In this example, T of n equals T of 2n by 3 plus 1, where 1 is the non-recursive part of the algorithm. From the recurrence relation, it could be deduced that a equals 1, b equals 3 by 2, and d equals 0. Solving the recurrence relation for the Master's theorem for the case a equals b power d, we get the time complexity of the recursive algorithm represented by T of n as theta of log n. To conclude, let me summarize the topics of discussion in this presentation. First, We discussed about recursive algorithms. Then we proceeded to mathematically represent the recursive algorithm by the recurrence relation. Then we solved the recurrence relation to obtain the time complexity of the algorithm that is represented by that recurrence relation. Thank you.